Namaste, welcome to Pythagoras Academy. This is Vikram Dachepally. In kinematics, equations of motion play a very important role. And most students tend to get into misconception when it comes to dealing with equations of motion. And when I say equations of motion, things that will come into your mind, maybe V is equal to U plus AT, S is equal to UT plus half AT square, V square minus U square is equal to 2AS. But let me tell you, these are not the basic equations of motion. These are just the equations of motion of one particular case. Let us try to understand the same. For constant acceleration, consider a case of constant acceleration vector. The magnitude and direction of acceleration is constant. In that case, so A bar is dV bar by dt, then dV bar is A bar into dt, and you are integrating on both sides. Say time t is equal to 0, initial velocity is u bar, and after some time t, the velocity is v bar. Now solve this integration. The very important thing is from this particular step to this. If you observe, I am bringing this A bar out of integration because acceleration is constant and it is independent of time. If acceleration is variable, it is a function of time, then I cannot do this. The equations of motion would change. So the set of equations that I am deriving here are valid only if acceleration is constant. Acceleration of the particle or the body is constant. Only then I can bring this A bar out of integration. Then solve it, integral dt is t, so from 0 to t, and finally I arrive at v bar is equal to u bar plus a bar t. This is the basic equation of motion. It is not v is equal to u plus at, it is v bar is equal to u bar plus a bar into t. There is a lot of difference. V bar is rate of change of position with respect to time. Again, apply integration on both sides and solve it. Finally, you end up with r bar is equal to u bar t plus half a bar t square. So this is the second basic equation of motion. R bar is equal to u bar t plus half a bar t square. So these are the two equations that are valid in case of constant acceleration of a particle or a body. Now let us try to apply them for different cases. I'll take a very simple case. Motion in a horizontal straight line, say case 1. The body has got some initial velocity u and acceleration a in the same direction. So the particle will move in the straight line only because acceleration is in the same direction of initial velocity. It moves along the straight line with increasing speed. So after some time, let me say the speed is v. So this is at t is equal to 0 and this is at t seconds. Now u bar, initial velocity, that is ui cap, and acceleration vector a bar is of magnitude a along positive x-axis, that is ai cap. If we apply the basic equation of motion, that is v bar is equal to u bar plus a bar t, because acceleration is constant, then I end up with v bar is equal to ui cap plus ai cap into t. So v bar is equal to u plus at into I cap. It means the magnitude of the velocity at that instant v is equal to u plus at. So this is where we get v is equal to u plus at. This is only one case out of many possible cases. This is one specific case where v happen to be equal to u plus at. Now you can also apply the second equation of motion, that is r bar is u bar t plus half a bar t square. So r bar I let it as x bar, it turns out to be ut plus half at square I cap. U bar is ui cap and a bar is ai cap. So this is what I get. The magnitude of displacement is ut plus half at square. And you have to remember that this equation x is equal to ut plus half at square will give you the magnitude of displacement but not distance, because it has come from the basic equation r bar is equal to u bar t plus half a bar t square, where r bar implies displacement of the particle. So x is magnitude of displacement but not distance. Of course, in this particular case, the particle is moving in straight line, so distance and displacement both are same. So there is no issue here. But you have to be very careful while applying this equation with the understanding that x implies magnitude of displacement. I can combine these two equations and substitute t is equal to v minus u by a in the second equation and derive a different equation that x is equal to u into, instead of t, I'll substitute v minus u by a plus half a t square v minus u by a whole square. Simple calculation, v minus u by a is common. Then I have u plus v minus u by 2, that is equal to x. So I am trying to solve it here. X is equal to v minus u into v plus u by 2a. So 2a x is which is equal to v square minus u square. The final equation is v square is equal to u square plus 2as or 2ax. This is equation number 1. Number 2, the combination of 1 and 2 is 3. This is not a special equation. It is just the combination of 1 and 2 expressing v in terms of x. V square is equal to u square plus 2ax. These are the three equations which are applicable in this case. Now if you take case 2, say there is a particle having initial velocity u in the forward direction and acceleration a in the opposite direction. U I cap is u bar and acceleration a bar is now minus a I cap. Magnitude a and direction is along negative x-axis. Minus, don't think that acceleration is negative. Acceleration is not negative. Acceleration has got magnitude a and it is directed along negative x-axis, that is minus I cap is the direction. If you use this in the basic equations of motion, v bar is equal to u bar plus a bar t, just as we did in case 1, we end up with v bar is u minus at I cap or v is equal to u minus at. Similarly, when you apply this in r bar is equal to u bar t plus half a bar t square, then you end up with x bar instead of r bar. So this is the case where the particle is moving in the straight line. After some time, it has got speed v, which is less than initial velocity, initial speed. Because acceleration is opposite, the speed is going on decreasing. Now x bar is ut minus half a t square I cap. So I have another equation that is ut minus half a t square. So these are the equations which are applicable in this case, and remember again that x is magnitude of displacement. Now there is absolutely no confusion whether you should use v is equal to u plus at or v is equal to u minus at. It depends on which case you are dealing with. And after all, these are the equations which are derived from two basic equations. And after all, they are applicable only for one case, that is acceleration is constant. Now combining these two, I can derive the third equation where I can substitute t is u minus v by a in the second equation, and I end up with v square is equal to u square minus 2ax. And when you deal with cases like projectile, a particle which is projected with some speed u at some angle theta with the horizontal, it traces parabolic path, it is a two-dimensional motion, but the acceleration of the particle throughout is g downwards, constant acceleration. So the two basic equations of motion are applicable even in case of projectile. Let us consider two simple cases like freely falling body. For example, Consider a freely falling body. Say there is a particle which is dropped from certain height h. Because it is dropped, initial velocity is 0. Because it is a particle which is freely suspended in air, it experiences acceleration which is g downwards. And neglect air resistance and other practical things. Let us consider the ideal case. Acceleration is g downwards, which is constant. I can use the equations of motion, and this freely falling body is nothing but case 1. It is like velocity and acceleration are in the same direction. So what will be the equations of motion in this case? So v is equal to u plus at, u is 0, so v is equal to gt. And displacement, so at any point of time, it has come down by traveling a displacement of y. It has gained a velocity v, so v is gt, and y is equal to ut plus half at square, u is 0, so y is equal to half gt square. In the third equation, v square is u square plus 2ax, u is 0, so v square is equal to 2gx. And what is the case of vertically projected body? Say a particle is projected from ground with a speed u up, and it is also having acceleration g downwards. So it goes to certain maximum height and comes down because the velocity is going on decreasing. At one point the velocity will become 0. After that again it is a freely falling body. So the particle goes to certain maximum height and comes down. Now what will be the equations of motion in this case? This is case 2, where initial velocity and acceleration are in the opposite directions. So v is equal to u minus gt, and y displacement at any point of time is ut minus half gt square, and v square is equal to u square minus 2gx. This is the proper application of equations of motion depending on the case that you deal with. Hope this has cleared all the confusion. Thank you so much. If you have any questions or queries or suggestions, you can always use the comment section to interact with me. I'll be more than happy to respond and receive your feedback. This is Vikram Dachepally signing off. Namaste.